Hi, I'm David Tower and you're watching the Theories of Everything program. In our previous program we began a new series, Theories of the Foundations of Knowledge. And in that first program we discovered how the scientific method evolved. And the scientific method has been a linchpin for a long time in our knowledge discovery process. We found that it evolved from earlier species, early primates, early hominids, early humans, from a process of trial and error, basically sifting through the patterns of their environment to discover methods that would be more conducive to their survival. In other words, patterns of hunting, patterns of which food to eat, patterns of how to live together socially, so that they could have a better chance of survival. And in the process they discovered a number of other things. They discovered the process of causality, that everything had a reason. They didn't understand all the reasons, but they gradually discovered, for example, that if they planted a certain type of seed before the rain, then that seed would evolve into a plant, would grow and produce other seeds, produce food. And they discovered certain patterns in the cosmos, and so that they gradually began to understand the seasons and the causality impacts of the seasons on their style of living, whether it was the impact on the weather, impact on their food, and so forth. So there was a huge sifting process going on, a huge trial and error process, which enabled early humans to survive better in a very, very complex environment. The process of trial and error, stemming from early neural reward systems, wasn't formalised until later in the last millennium, and around about the 17th century, by Francis Bacon, who gradually was able over time to abstract the key processes within a larger process that would allow information of value to be discovered, to be tested, to be analysed, and from that analysis to provide predictions into the future, because this again is the basis of survival. No one said at that time, let's get together a method that can sort of formalise our process of discovering and proving and verifying knowledge. What happened was that over the millennia, a number of factors came together, and out of that a number of factors of understanding the process of knowledge, verification, and the process of truth, which we discussed in the last program, to enable this abstraction process to occur. Now, the first part of that process one might call the discovery process. Now, in earlier times it might have been the discovery that red berries made early humans feel very unwell. And perhaps they tried a number of different berries, and every time they tried a particular type, or every time the berry happened to be red, or the food source, plant food source, was a red type, then they had some unpleasant consequences. There seemed to be a causal relationship. So out of that they were able to infer that they should avoid red berries wherever possible, no matter from what particular source. The same thing goes on in the modern scientific method process. There is initially a knowledge discovery component, and it takes a number of forms. It might be in the form of a very fuzzy hypothesis. The hypothesis might be something that someone's or a group have mulled over for a long time. It might be a new energy source, it might be a new form of transport, whatever. Or it might be something that almost comes out of the blue in the form of a flash, but usually those two things go together. It's usually the result of a person or a group thinking about a particular problem for a long time, and suddenly that problem gets crystallised, or an answer to that problem gets crystallised. Now this happened a large number of times in the past. In fact, it's happened more often than we know. But Einstein, for example, had the flash or visualisation insight of riding a light wave. Now, there's a lot of mythologies written about Einstein, and maybe this is one of those, but a number of sources have attributed this particular visualization flash to Einstein, and from that his conception of the special theory of relativity possibly evolved. And one of the greatest instances, of course, of a flash was arguably the greatest mathematician of all time, Ramanujan, a young Indian who was relatively uneducated, had read hardly any mathematics, but had this incredible genius for mathematics, and he basically developed hypotheses, theories of mathematics in his subconscious. He virtually dreamed them. And he dreamed up in his very short lifetime, he died of tuberculosis in his early 30s, 4,000 very complex mathematical theorems, each of which would take a very good mathematician at least a year to sort of fully validate and fully test. So that was a sort of extreme type of flash. But the other aspects of the early formulation of hypothesis comes from an aesthetic angle. The process of truth and beauty as a means of discovering truth, or an aesthetic type of approach to the discovery of truth has occurred a number of times. Occam's razor, of course, is a principle that says that if you have two theories, for example, the early theory of the sun revolving around the earth, or the alternate Copernican theory of the earth revolving around the sun, they both were explainable in terms of data. However, one was more simple. the early one, the geocentric theory, required quite complex epicycles to be formulated to be able to predict the motion of the planets, while the other one didn't. So the more elegant, the more aesthetic proof is the one that usually wins out in that situation. The search for truth, as mentioned in the previous program in the series, is a very tricky process indeed. We discovered just by talking about coffee that various statements made about the drinking of the coffee, the aroma of the coffee, the quality of the coffee, the quantity of the coffee, etc., are impossible to verify based on simple statements of that type without understanding the context, the subjective context of my statements, the space-time context in terms of events that occur with that coffee and drinking of it, social context, whether people in general assume that coffee was a good thing or not. Context is everything, history is everything, we'll find when we're looking for truth. We needed to know, for example, the history of coffee in that particular cup to verify the statement that there never was any coffee in that cup. It's a nonsensical statement based on its current state. We have to know, we have to be able to look back into the past. We'll see in our next program, in fact, that this is an extremely important idea in verifying truth. We see, in fact, that this coffee cup is a snapshot, this object is a snapshot frozen in time. The truth about that coffee cup extends across its whole history. The truth about you, the truth about me, the truth about any object requires a continuum of understanding, to put it in context. So early humans, of course, were struggling. Here they had this enormous, gigantic universe around them, all the things on Earth. Gradually they had to discover about the cosmos, they had to discover the motions of the stars and planets, the significance of them. They attributed them to early gods, but they did understand, gradually were able to sort through the patterns and understand the seasons and the motions and the cycles, planets and stars, the moon and the sun. The matter around them, what was it made of? Gradually over time it was understood that it wasn't fire, earth and water and air. It was individual components, tiny components. Later it was discovered, of course, that those components had subcomponents in them, had protons and electrons and neutrons, and later it was discovered that those components had further subcomponents in the form of quarks. There are other amazing particles made up of those quarks. Pions, for example, there are other particles that went hand in hand with electrons, such as neutrinos, etc. And emerged a theory of matter, a theory of forces and a theory of matter, and controlling those components. And then later, the latest theories of string theory, for example, says that all particles are made up of little energetic strings of matter wiggling in space-time. Those little energy fields create particles, and there are more and more discoveries being made every day about the nature of matter. It brings up a point about theories. People often say it's just a theory. What they're saying really is it's just a hypothesis. There are two types of theories. There are good theories and bad theories. The good theories are the ones that have a lot of weight and evidence on their side, and they can be applied to predict useful things for humanity with a fair degree of certainty, if you like, a fair degree of truth. Bad theories don't have that. Bad theories fall by the wayside because their value is seen to be marginal. And those theories may be completely tossed out or amended. Many good theories, early theories of Newton's theories about space, time, gravity, forces, acceleration, mass, etc., inertia, are still in play today. Einstein's theory, as I've said several times, extended that theory, but the original theory was fine within its context, within its frame. Once you got up to higher speeds, Einstein's theory kicked in, and once you talk about major issues in the major objects in the universe, such as black holes, Newton's theory drops away, but it's still valid in certain contexts and still valuable, extraordinarily valuable to humanity. So theories evolve. They continually are amended, continually refined, and that's the nature of them. So to say something is just a theory is really a nonsense. You have to again look at the context and the veracity of the evidence supporting that theory. Now, early humans did this with, gradually got their state of the environment understanding together, and that wasn't just about the stars or matter. It was about life itself, how the human body functioned, how the mind functioned. And all these theories are still evolving today, but at a greater rate as the evidence pours in to support the leading contenders. Once good theories evolve, they are usually shared for the benefit of the tribe or the larger group. Sometimes the same theories are discovered independently, as in different early civilizations across the globe. However, before knowledge can be shared, it has to be codified. And it was codified again with the major driver being early agriculture, again around 5,000–6,000 years ago. Numbers evolved to codify the amount of and the quantities of crops, animals, etc. Alphabets evolved and turned into writing processes soon after. Alphabets evolved so that narratives could be written regarding information that was gleaned, and again later it evolved as religious information, cultural information. In the beginning, of course, it was applied just to provide, for example, a signature, a notation to show who owned what particular quantities of early goods. So the codification took place, and of course that accelerated through the ability to print information, to duplicate it, so that it wasn't just owned and controlled by a small number of scribes or priests, and it could be shared across the globe as it was, as travellers and traders crossed different civilizations. They took this knowledge with them and brought knowledge home, as well as goods. And of course today's internet spreads the knowledge very quickly and has some enormous potential beneficial outcomes in terms of being able to share useful technology, useful understandings, again not just new ways to do things but also new understandings of social practice, good governance, human rights, etc. across the globe. Another way of codifying knowledge, of course, and one that started very early on for early humans, was art. The visual process. By being able to paint and draw in early caves to start with, body paint for example, as well, they were able to get huge amounts of information across quickly to others in their tribe or clan. Information about hunting, information about religious processes, religious protocols, information about life in general was able to be transmitted to others very quickly, and the same goes today. Mathematics, which evolved of course from the early adding of these numbers together, multiplying them together to calculate amounts. Mathematics isn't the only way to codify information, and writing procedures down isn't the only way either. A visual hit from, for example, Picasso's Guernica painting, the oral hit from a Mozart or Beethoven composition, or any other form of art that comes through the senses, is a valid and alternative approach that society has continued to develop over time. So there are a number of ways that knowledge can be codified and distributed. Originally, of course, it was by word of mouth, travellers. Again, later it was electronically and through early forms of Morse code, etc., and by printing, and again today via the electronic internet. More sophisticated theories really began to evolve around 2,500 years ago with some of the more rigorous developments in mathematics by the Greeks, by Euclid for example, developing a number of theories regarding simple mathematical objects that stand to this day. And of course around about the 17th century, theories of the physical world began to take shape, primarily with Newton's theories of forces acting on matter, forces producing acceleration, and the first unified theory of gravity, which unified gravity on the Earth, for example an apple falling to the ground, with celestial theories of gravitation, the moon revolving around the Earth, for example. Newton brought those two aspects of gravity together in an extremely sophisticated and critical theory for the time. Now from that point, a number of other theories, major theories, evolved. These might be called unified theories, a unification of a lot of the bits and pieces that had occurred over the previous several millennia. Those theories, apart from the mathematical theorems, but theories about how species came into being, theories about how the Earth began, theories of what the stars were, for example, were in very early phases up till again the beginning of around about the 16th century, when a number of other developments assisted in the process. For example, the development of early telescopes, microscopes, etc. And other theories about how the body works, of course, was also bubbling along. But around about, say, 200 or 300 years ago, these theories started to take on a much more rigorous form. And also at that time, of course, the scientific method was formalised as well. So an understanding that theories had to be tested in the cauldron of life by peers, by peer scientists, before they could be accepted, took shape. So we have a number of major theories. A major one, of course, that supported the developments in steam power was the theories of thermodynamics, and which included theorems of conservation of energy, that heat and work were different forms of energy, but they were conserved. You couldn't lose that energy. And theorems about how hot bodies became cold bodies, theories of kinetics, etc. Theories of electromagnetism took shape as well. Of course, I mentioned earlier the theories of Maxwell. Earlier than that, there was the wave theory of electromagnetism was developed by Huygens. And there are a number of developments before that with Faraday understanding lines of force around a magnetic body. These were the first unified theories, gathering bits and pieces together into a more solid, more holistic form. And of course, at the beginning of the last century, we have theories of relativity, which really got to grips with space and time, and a new formalisation of gravity. And after that, quantum theory, which was the first attempt to really understand what was going on at the subatomic particle level, at the basic constituent level of matter. Of course, the grand unified theories that were evolving in the 17th, 18th and 19th and 20th centuries weren't all about space-time and matter. They were also about life. And of course, the most important and perhaps the grandest of all was Darwin's theory of evolution, which explained the way that different species came into being, the way they evolved. Now that theory and all the others required proof. And so most of the 20th century, and now also in the 21st century, there is a continuing emphasis on proving and refining these theories. So a lot has gone on in the last, particularly in the last century. Einstein's theory of general theory of relativity, which explained gravity, was of course the first proof came in from measuring during a solar eclipse the bending of light around our sun from a distant star. The proving process still goes on with standard theories of matter. The standard theory, as it's called, was missing until very recently one particular component called the top quark. There are three families in this standard model, but one of the components hadn't been discovered in the collision chambers that are used to, in the colliding detectors that are used to verify whether these particles actually exist that are predicted by theory. But that top quark has been found, for example, recently. One of the most powerful methods of proving theories is in the form now of computer models. Computer modelling is a standard component, a standard part of every scientist's toolkit. The models are usually in the form of differential equations through which, and they're a very abstract form obviously of proof, and they're applied to things like the weather, things like understanding how proteins fold, for example, understanding turbulence in fluids. But they're systems of equations in which various parameters are set according to the theory, and through which data is pumped and the outcomes verified. And this is applied also to theories like evolution and genetic theories in general. Theories of heredity, for example, used computer models. So these models have been able to verify, for example, how the sun first formed, how galaxies formed, how life evolves, and all the other complex, how light reacts in certain circumstances, and of course all the environmental phenomena as well are modelled. So the computer has become an extremely important tool, not only in business but in science, to verify the truth. Despite all the knowledge gained by humans since the beginning of civilization, theories of complexity and chaos and randomness in our knowledge base, in our universe, and uncertainty are beginning to emerge, which really need to be factored into our foundations of knowledge if we are to proceed to the next stage. So we'll be looking at some of those aspects of the random and uncertain nature of knowledge and the universe in our next program. I'm David Tao, and you've been watching the Theories of Everything program. I'll look forward to seeing you again next week.